Lab 4 Circuits by Pablo Vila. The main purpose of today's video is to predict the behavior of circuits containing resistors in series and parallel. We'll also use multimeters to measure the current and potential difference of different circuits. And finally, we'll examine the behavior of capacitors and resistors. The main lab results we will see by the end of this video include 1. Node rule and loop rule hold true, and 2. RC is dependent on time. The main physics ideas that are present in this experiment include the loop rule, delta V round trip is equal to 0, node rule, I in equals I out, and Ohm's law, which is V equals I, the current, times R resistance. The procedure in this experiment includes creating multiple circuits using the virtual lab kit, including series, parallel, and RC circuits. Next, we measure the voltage and current across different sections of the circuit by using a voltmeter. Finally, we graph our results to find any trends and understand the circuit more. The initial conditions include attaching a two 1.5 volt battery to a 47 and 100 ohm resistor, along with attaching two ammeters. The system in this experiment is a circuit, while the surroundings include everything else. When connecting the battery, resistors, and ammeters in a series, the current remained at a constant 0.02 amps. Reversing the direction of the ammeters showed negative values. In circuit 2, a voltmeter replaced an ammeter. The voltmeter read 3 volts, while the ammeter remained at 0 amps because the circuit was now opened. Next, the potential difference was measured between different points of the circuit. From point A to point B, the potential difference was 3 volts. This value also represents the EMF value of the battery. The points from BC, DE, FG, GH, and HA all read 0 volts because the potential difference of a wire is so small that it is negligible. CD and EF, however, read negative 0.96 and negative 2.04 volts respectively. The reason they are negative is because the potential difference is moving in the direction of conventional current. Since a round trip must equal 0 volts by the loop rule, we know the value's total potential difference must sum to 0. Using the same circuit as before, we can confirm that the resistors are equal to 47 and 100 ohms using Ohm's law, where we can divide voltage by current. The wire and ammeter, on the other hand, still have a resistance of 0. Next, we want to analyze the potential energy throughout the circuit. As mentioned before, wires have negligible potential difference, which is why the graph remains constant throughout those points. Between points A and B, the potential energy raises to 3 volts. Between points C, D, and F, the potential energy drops back down and eventually reaches 0 once it makes a round trip. At point GH, we can see the ammeter reading remains at 0 when attaching a voltmeter. This is because the voltmeter resistance is large and little current flows through it because current likes flowing through the path of least resistance. Next, we add an extra ammeter in parallel to the 100 ohm resistor and find that the overall current increases. Again, the reason for this is because ammeters have very low resistance, so most of the current at the node flows through the ammeter because there's less resistance there. Next, we build an RC circuit and notice that the light bulb quickly dims as the battery charges the capacitor. Removing the battery lights the bulb again and discharges the capacitor. When testing the charge and discharge time of the capacitor at different resistance, we can see that the resistance of a 10 ohm light bulb is twice as fast as a resistance of a 20 ohm light bulb. Finally, we can graph our results by timing the capacitor discharge time for a 9 volt battery, 2.5 farad capacitor, and a 30 ohm bulb. After linearizing the data, we can divide 1 over the slope and get an RC experiment value of 5.984 seconds. The predicted value is found by multiplying the light bulb resistance by the capacitor to get 6 seconds. The values were very similar, with the data having only a 99.74% accuracy. What if you used an actual ammeter instead of an ideal simulated ammeter? The current reading would be lower because ammeters don't actually have a resistance of 0 as simulated in the online lab. So what if you use a real battery to charge a real capacitor with no resistor in the circuit? Capacitors would not start charging instantly like they did in the virtual lab. Instead, it would take a moment for them to start charging. In conclusion, we can say the conservation of energy principle applies to circuits through the node rule and loop rule. We can also see that capacitors charge and discharge. Some potential sources of error for this experiment include online resources that are not accurate to real life. Resistance at current measurements might not have been measured accurately, And finally, the capacitor discharge time might not be exactly what would you expect in real life. Thank you for watching this video. Please make sure to subscribe and smash that like button so I can continue making videos like this. Thank you.